My presentation, the title is Towards Trustworthy Neural Network Models, a Neural Network Intrusion Detection for Web SQL Intrusion. And you know the internet is the most complex machine humankind has ever built, so it's very difficult to defend it from attacks. And with the growing popularity of the QUIC protocol, QUIC protocol, which all the package header information are hidden and encrypted, even the IP address is scrambled. So the traditional intrusion detection method has failed and not feasible anymore because we relies on package header informations. So more and more researchers have to use machine learning to dig patterns from history data. In other words, we can only guess. But machine learning is a black box model. They cannot explain their decisions, especially neural network models, which are known to be fragile. Even trivial disturbance on the input dataset can make the output tremendously fluctuated and without any explanations. In domains where security is of utmost importance, like the cybersecurity, trust is a fundamental basis and guarantees of its validity. People's trust in the decisions made is based on the interpretability and the transparency of the machine learning models. Unfortunately, most of the popular machine learning models, especially deep learning, big models, and even the tree-based models are uninterpretable. The consequences of the decisions made on uninterpretable machine learning models are occasionally catastrophic. I will come back to this point later. The novel intrusions like the dataset poison and the counterfactual models, it's very easy to fool our deep learning models and without any explanations, and people are not even be able to know it, especially with the QUIC protocol. This poses high risk to the public security, and the people are not even aware of it. Maybe some people have heard about this famous jokes. But years ago, a very famous university in America, they used a deep learning model to successfully identify husky and dogs, husky and wolves. I'm sorry. It's very famous, and it's come to the news everywhere. It's another big success of deep learning models because even humans it's difficult for humans to identify husky and wolves. And when the explainable AI technology came out, people want to know what rules has the model learned. How did it identify huskies and wolves? So they explained the model. And it turned out that the model did not learn anything about wolves or huskies. He learned only how to identify snow. So he successfully identified husky and wolves because it learned if there is snow in the picture, it is wolf. Otherwise, it's husky. Because all the pictures with wolves in the training data set are that wolves are in the snows. With all these numerous explainable AI technologies, I have to point out not all explainable AIs are trustworthy, because the current many explainable AI technologies are built on empirical data. They use simpler models to simulate the complex models and to drag in explanations out of it. But this kind of explanation is vague and is not determinism. It's not stable. Which means if you try the same technology and the same model at a different time or different platforms, it may come out with different answers. So there is another kind of explainable AI technology which are called rigorous explainable AI, because it's used formal method. And there are many different kinds of rigorous explainable AI technologies, but the basic idea are the same. We treat the model as a chip, and we map the logical explanations out of the model, and we drag the prime implicant from the logical expressions. And in this way, because every step of the method are formal method, so it is guaranteed to be accurate, which means it is 100% loyal to the model. However, extracting regrowth explanations is NP hard, because converting each individual neuron into a Boolean expression, it is an NP hard problem. And representing the Boolean expression into the more trackable representations is an NP hard problem. And extracting prime implicants from the Boolean expressions is also an NP hard problem. So many years of effort has been devoted in relaxing these problems into trackable ones. But the regrowth explainer model suited for continuous features has still yet to be invented. Here is examples of regrowth explanation. As many of machine learning researchers, they know the first examples that try explaining machine learning is to identify handwritten numbers. Like these numbers on the left, this model has successfully identified this handwritten picture as 1, and the regrowth explanations are shown in the middle, which means, look at these pictures in the middle on the first row. If these 2 dots are white and the 3 black zones are black, the other gray areas don't care. I don't care what the gray areas, the value is, because it doesn't change my decision. So I don't need to carry out experiment to know the picture on the right, no matter how it is an obvious 0 to our humans. But we know the model will 100% identify it to be 1. Because it is 2 white dots, it is white, and the 3 black zones, it is black. And the same here on the second row. The model will identify the left picture as 0 because the reason in the middle pictures, because the 3 white dots are white and the other zones don't care. These are prime implicants extracted from the model. So we do not need to carry out any test on the right pictures to know, no matter how it is obvious 1, but the model will in the middle as white, and the other dots don't care. They won't change the machine's decision. So let's give some formal definitions. The implicants, as we may already know, it is the proposition formulated in a term that satisfies the knowledge base. It means the thought implies the knowledge base. And we also have structuredness. The definitions here is saying that we are using formal method, which are logical, formal languages, logical languages, to represent the model, and then we extract the prime implicants out of the logical expressions. Although it is very complex, but every step is formal, so it's 100% accurate. It is guaranteed to be accurate. And it does not change whenever you every time you try a different platform or different languages. So it means a lot to intrusion detections, because sometimes we use a binary expression to represent the network flows. So in binary strings, even error in 1 bit can lead to huge misunderstanding and misleading. So we need to be 100% accurate. We need it to be formal. There are some subtle differences between sufficient reasons and prime implicants. It's just the prime implicants provide the global explanations of the whole model without not to any specific flows, but a sufficient reason disclose the local explanations. I'll give you a demo later. Here is a brief state of the art of explainable method. As you can see, the majority of them are empirical, which means are not formal. And the formal explanation methods are very few. Most of them are linked to Professor Edwin Dulwich in UCLA and some other researchers in Washington University. Here is a brief summary of explainable AI used in intrusion detections. All of them, so far in my humble knowledge, are not regrowth. There are empirical, explainable AI technologies. Here is the architecture I proposed. Basically, I grab the network flows, use CIC flow meters. I take statistical features out of the network flows because the head packages are no longer available to quick protocols. And then I extract the statistical data and get the features out of it. And then I train the neural network model out of it. And then I treat the model like a chip. And I represent it, use multi-value logic and treat the model into a huge logical expressions. And then I propose a method, a heuristic that can swiftly and quickly extract the prime implicants out of the logical expressions. And these prime implicants are represented as my explanations, both global and local. The basic idea is that I have the formal definition of the model. I treated it like a linear classification equation. So my model, after I convert into use the formal method, is like a huge equation below. It is huge, but it's a linear classification equation. So the whole model can be represented formally by this single equation. Then in my heuristic, I define an always pass zone and an always fail zone. And I find a way to swiftly find the division of these two zones. Those divisions are the game-changing point, which are also the explanation of why machine made the decisions. The heuristic can be roughly explained in this algorithm. This algorithm uses like 3 features models, but it can be easily expanded to any number of features as you like. And the model I have trained with real data, real Web SQL injection data. Have the feature information value are like this. All the information values are about 0.5, which means it is very important. And the position record curves of the model is shown like this. It is pretty much, it's not bad, right? So I want to know what it has learned. This is what it has learned. This is a demo. It's a local explanation of one specific network flow. This network flow, after represented in the multi-value logic expression, the value is shown here. And I divided the value into positive value and negative value. So the positive value are shown in red, and the negative one are shown in blue. And I can explain it in plain language, plain English, like this. This one of these explanations says, if only the instance could change its features to G over 5 and D over 6 or 8 and U over 9, then the other features stay the same. The model will change its decision and classify it to the Web SQL injection. And we can even further translate it into plain English. If only the instance could change its feature to forward package length standard to about 253.8.7 and forward header length about 6183826 and the package length minimum below about 496. While the other features stay the same, then the model will change its decision and classify it to Web SQL injection instance intrusion. Here are some examples of the global explanations. As you can see, each rules extracted from the algorithm in less than 0.00 seconds. So it's really swift. And these are the texts in red are the global explanations, and then I translated it into plain English. For example, these explanations are working presented as rules for the model to make decisions. Like this one, if the instance negative input have H below 2 or A below 3 or blah blah, and the other negative input equals 1, then whatever the positive input are, the model will classify it as Web SQL injection. And there are some other rules of which you can find more details in the paper. To compare with the state-of-the-art explanation technologies, I explained my model with SHAP. It is one of the most popular state-of-the-art explainable AI technologies. Here is the outcome. As I said before, it is not a rigorous explainable AI, so it cannot provide very precise explanations. It can only give you a vague impression of how important these features are. So this is its explanations. And I have compared this SHAP explanation with my method with the time overhead. As you can see in the table below, in my feature, every rule I extract is less than like 0.001 seconds. Or in the worst case, it's like 5 seconds. Or when the feature has the feature number is the maximum 8, which means I considered all the features at the same time, which is the worst case, and which means and then the biggest time overhead is like 400 seconds. But the SHAP method takes hours, and it can only use like 100 instances. It didn't take all the data set into consideration. I tried it before, but it's overlapped. It's Stack Overflow, so you can only consider a very small fraction of the data set. So after you have looked into the model and see exactly what it has learned, what's in your mind now? I did my thinking. I think a little. The most impression to me is that the model didn't care about semantics. It didn't care about numbers, because in its essence, it is an equation. An equation only knows the numbers. It doesn't care about what the feature's semantics is. Does it make sense? That is rational? It doesn't know. It doesn't care. Although we can build semantic web, like we gave it a big model, we told him what the concept relation is, like what is give it a knowledge graph, and make it seem to humans that like ChatGPT, like he knows what a semantic is. But that is an illusion. That's not real intelligence. The machine is a machine. Deep inside, it only knows 1 and 0s. It only cares about numbers. This is a graph from a PhD student thesis, Qianru. From this graph, we can see that all the data we can collect are history data. All the data we can consider are from the past. And no matter how good the machine feeds into the data, the future, is this for the machine to tell? No. The future, the machine can only feed past. It cannot tell you the future. The future is created by humans and humans only, because only human has imagination and has the free will. The future is created by humans, and the future has any kind of possibilities. So, as we can say, all models overfeed. You cannot have any model that is not overfit. All models overfit. And even it has 100% accurate to the history, it doesn't mean anything for the future. Maybe in some domain, like the facial recognition, there are some features that people don't change with the time, like your face, like your bone structure. It doesn't change with time, so that's why we can use machine to learn to recognize your face. That's some kind of domain. In a small error domain, you can use the machine learning can again really success. But the machine learning, as we can know, it's not restricted to facial recognition. It is all over our society, all over our life. It is predicting our future. It is studying us, studying humans. It focuses on humans now. It studies our psychology. It studies our future, study our human behavior, and telling whether thank you, whether we will be a good employer, whether we will be a good lover, we will be a criminal. It is our life is pervading with machine learning models, and we don't know what is learned, and we don't ask questions. Because the big models are disguised in huge, complicated mathematical equations, it scares people away. Nobody dare to ask, and nobody, maybe through their entire life, they didn't know. Mathematics here is not a tool for solve problems. It creates problems. It disguises the big models. If we are researchers, and many of us have practiced the machine learning model. If we can remember what do we do when we are building a model, if we would like to build a model for a certain question domain, what do we do? First, we think of some features that we think in our instinct that may be important for this domain. And then we send people away to find some measurable parameters that can represent these features. And then we assign some weights to these features randomly. And then we grab all the data, history data that can train the model to twist this assignment, twist this weight to make it fit into the data set. So the machine learning models, although it is represented by huge, complicated mathematical equations, it is personal, objective point of views. It is point of view of some kind of people, not the real truth. So we are all researchers, and now we will do scientific research. What do? We do measurement. A question is it no measurement? Is it no scientific if there's no measurement? But all the measurement features of machine learning are the measurement for other metrics for data sets, not for the model. There is no single one of metrics as a metric for the models. All the precision record curves, all these measurements are describing the data set, a single specific data set, not the model. Without measurement, there's no science. It is not even a scientific question. How do we let a scientific question, it is post-scientific questions. How do we let it overwhelming scientific academia and even the society? We now let the models to pervading into human societies all everywhere. So the models are controlling our humans now. When we let the model to control our life, the model is playing God to us. It decides which do we CV pass the HRs? Will we get a good job? Are we a good lover? Will we be a good criminal? Can we get the loans? It's controlling our humans, and most of people have no clues of that. The machine is treating us like they at his own will, but we humans don't even know about it. As a machine can only learn from data, and all data are history. So the machine, if we let the machine control our future, our life, then we will let the machine will stuck us into the past. We will be repeating the patterns in the history. There is no innovations. There is no futures. We'll be stuck in the loop of the past. Do we really like it? So the machine models will make the people rich in the history richer again, and will make people who are poor in the history even poorer. It will make the people who couldn't get a job even harder to get a job in the future, and make a person who commit crime in the past has no way but to continue committing more crimes. Is this democracy you want to see? is this really bring humans more democracy and more scientific as a medium has persuading us? Think with your heart, not listen to the internet. Because as the data said, a majority of the internet messages are from the AIs. Even the majority of the human of the account, not just Twitter, Facebook, but any kind of platforms, majority of the account are not humans. There is a one the AI has become the top risk into 2020 in current days now. And do we know the high-end hunters often appear as a prey? When we are taking advantage of the internet, when we are taking advantage of the AIs, how do we know the AI is not consuming us? Our ideas, our point of views are shaped by the internet. And human thoughts are easily shaped, are easily misleading, because we are very easily persuasive. And what's worse is that unlike humans, the machine never know that it made a mistake. Although we human has many fragile or something like that, but we humans know when we made a mistake. We know we have a point of view. We are humble. But the machines, we cannot teach them to be humble. It is a machine. It's a tool. It can only execute the code. It will not learn democracy. It will not learn how to be fair by itself. It cannot learn it from the data. Only humans can codify it to him. But the manipulators of the big models, will they let do they care about whether the machine has mistakes? These are people, they only care about money. If we still let these kind of people who don't care about money, they will undertake risks. It is their habit to undertake risk and to tolerate certain kind of errors or mistakes, so long it makes its own more money. If we let this happen, what the future will be? Okay, this is my talk. I'll take any questions.
Thank you very much, Dr. Qianru. So we have time for maybe one question from the audience. Yes.
I agree with you that a lot of the models are opaque, hard to look into, but is the science going forward in terms of being able to understand how the thing made its decision, or can we train another neural net to talk to the first neural net and find out what it was thinking? What's the research there?
That's why I'm thinking about philosophy questions, because if this question in this philosophy is unanswerable, it has no end, then no matter how hard we try, it is impossible. Thank you.
Okay, thank you very much.